So let us start the session. So uh, today is our last session, and I hope you've learned from this course and these video sessions have been helpful. So let us start today's session. Okay, so I'll start with question 6 first because first few questions are little typical. So I'll try to do them at the last. So let us first see question number 6. Okay, so in this question, what they have said that we have an inductor and a capacitor connected uh, in this circuit in this through with this MOSFET and a load. So here what they say that is the inductor and capacitor are large such that the current through the inductor is constant. That is a constant current flows through this inductor, and if a constant current flows through this inductor, we know that okay, so there will be no AC in this inductor, and a constant voltage flows across the capacitor. That means the voltage across this capacitor is constant. So what does that mean? That uh, so through this path, like here, if we assume, let's say, at low frequency, the inductor will be uh, open circuit, and at high frequency, the inductor is short. So if we see that this capacitor would be charged with VDD, right? So a constant voltage, because there is no uh, between this inductor and capacitor, there is no resistance. So this VDD cannot drop. So the there will not be any loss in between this. So the capacitor will charge with VDD. Okay, so let us see what the question asks. The question says that the maximum amplitude VD says that the device is in saturation. Okay, so let us see this. Just a minute. Okay, so if we draw the circuit again, we say here it is VDD. Okay, so it is given in the question that VG is VT plus VGST. So this VGST is nothing but uh, the extra overdrive voltage that we give to keep the transistor in saturation. And to keep this in saturation, this voltage, the minimum voltage across this should be this VGST, right? So okay, so we know that VD, okay, VD minimum is, let's say, overdrive voltage equals to VGST. It is given as 0.15 volts, right? And if this voltage is at 0.15, and here it is capacitor is charged at VDD, and it is constant. It is said that it is constant, right? One, somebody is joining. Yeah. So yeah, so the voltage across the capacitor is constant. So it is here it is 0.15, and here it is VDD. So that means this VD is what? So VD equals to VD minus VDD. Right. It is 0.15 minus, and VDD is given as 1.9 volts. 1.9. So it is the value of VD. So it will be the minimum value of VD. So so VD is what? VD, this small VD is an AC voltage, right? So if this is the minimum value, the maximum value will be the negative of this. If it is 0.15 minus 1.9, it will be 1.9 minus 0.15. So VD max is 1.9 minus 0.15 equals to 1.75 volts. Okay. And I think that is the answer. Yeah. And this is the answer. Um, any doubts in this part?
No, sir.
Okay. So just remember this thing, then take its opposite for maximum, and you will get your answer. Okay. So let us see the next part. So in the next part, uh, while the amplitude of VD is maximum, what is the maximum amplitude of ID? So the device is on. Okay. So let us see this. Just a minute. Okay, fine. So let me copy things from here. Let me copy this page. So now we know that VD min is this. VD max is what? VDD minus this VD is what? VGST, right? So therefore, ID max will be what? Let me delete this. ID max will be VD max by R, right? ID max, ID, this ID is the current flowing through this, so it will be maximum when VD will be maximum, and it is simply VD by R. Okay, so let me draw. It will be 1.75 by R. R is what? R is zero point 0.9 kilo ohms. It is, yes. And if you solve it, it will come out to be 4 milliampere. So this will be ID max. Yes. So in this question was easy. We already knew VD max. We just divided by R to find ID max. Okay. This fine.
Yes.
Okay. What is this? Okay. So now what they're saying that the current ID is GM times VG, and we have to find the required GM for this maximum ID. Okay. So we know that here ID equals to GM times VG. Okay, and ID max, we already know it was 1.944 milliampere. and for this value VOV was 0.15 volts, right? So we know that GM equals to 2ID by VOV. So we have done this earlier also. This formula GM equals to 2ID by VOV. Uh, Let me do it simply. GM equals to K VOV square, right? So LID by del VGS into GM 2K 2K VOV. So GM equals to 2K VOV. We can do into VOV upon VOV. So this thing is what? ID. So GM equals to 2ID by VOV. So we will use this relation here. So here 2 into 1.944 milliampere on 115 volts. It will be, let me check. Can any of you please solve this? I am getting it as 25.9 millisiemens. Please see if it is correct. Uh, are you getting the same thing?
Yes, I'm getting.
Okay, I am not able to hear you. I think there is some network problem. Give,
Getting, sir.
just, just give me a minute. I'll reconnect my audio. Am I audible?
Yes, sir.
Okay,
Yes, sir.
fine. So I hope this is correct. 25.9 millisiemens. Uh, yeah. Let us move on to the next part. Okay. So now ID equals to K VGS minus VT. That is VOV only. Okay. What is the corresponding K? So this is again easy. ID equals to K VGS minus VT whole square K VOV whole square. K equals to ID by VOV square. It is 1.944 milliampere, 0.15 volt. Sorry, 15 square. So if I solve this, so I'm getting here is
86.4
86.4.
millisecond.
Yes, 86.4 millisiemens per volt. This is the answer. So this was also easy. I hope there is no doubt in this. So let us move to the next question. So next question is, what is the efficiency of this power amplifier? So that is the power absorbed to power delivered to power absorbed ratio. And you have to give the answer as percentage. Okay, fine. So if we look back at the circuit, this was what VD, ID, VDD, ID, right? So okay, I okay. So power uh, delay power, let's say power absorbed from load, from source, right? From source will be simply VDD into ID. It is what VDD is 1.9 into 1.944 milliampere into volt. So let it be. I did not solve it. Write it like this: milliwatts. Right. Power delivered will be VD ID. So since VD and ID are AC voltages, we can do is take their RMS. So by root 2 by root 2. So these are the peak values, right? So by taking root, we have taken their RMS. So it will be VD was what? 1.75 into ID was what? 1.944 divided by 2 milliwatt. So if we do ratio power delivered to power absorbed, that is P del by P ABS equals to 1.75 0.94 by 2 into 1.9 into 1.944 cancel. So it will be divided by 2 into 1.9. It will be 0.46. It is 46% is the power efficiency. Is this clear?
Yes, sir.
Okay. So let us go back to question one then. Okay. So in question one, this is a schematic of voltage regulator circuit, and the dirty supply means that it will have some. It will not be constant. Let's say 1.9 volt something. It will have some ripples or fluctuating voltage here. And okay, the op amp, this op amp has gain of 13919. This is the open loop gain. Let me write it. R1 R2 are given, and op amp output resistance is 399 kilo ohms. Okay, what is the output resistance of complete voltage regulator? So let us see how to solve this. Okay, so let me draw the op amp. Let me draw it a bit bigger. This positive, this is negative, and let's say I'll draw the internal small signal circuit inside the op amp for reference. Okay, say this is VD, will be A times VD, and it will be Z out. Yeah, this is this. Okay, now we have connected what? R2 and R1. Okay, and this is connected somewhere, but doesn't matter here. This is the VDD. Okay, so let me write it as Z not only. So we are given with 1319 Z naught equals to 399 kilo ohms, R2 R1 equals to 23 19 kilo ohms. Okay, is anything else given? Nothing else matters. Fine. So we know that when we want to find the output impedance of any circuit, we can add a test circuit. Say I take current V and let the current I flows through it. So this I will be divided in two parts, right? I1 will go here, I2 will go here, right? So, okay, fine. So let this voltage be V1. So what is V1? Equal to R1 by R1 plus R2 times V. It's fine, right? And okay, this is V1. Okay, fine. Yeah. And I1 is what? V by R1 plus R2. Okay, so okay, for now let us okay. This so here when we are connecting this V here, everything else is connected to ground. So what is this VD here? So we see VD equals to 0 minus V1. It is minus V1, right? And it is minus R1 by R1 plus R2 times V. So here what will be A times VD? So let me redraw this part in the next page. It is something then C AVD Z naught, and it is connected here to this Z naught is connected to this test V. V somewhere I okay. So what was VD? Vd was minus R1 by R1 plus R2 times V. So AV will be simply this. Uh, Let me write it here. Minus A R1 V by R1 plus R2 is the voltage here. V is the voltage here. Then current through Z naught, that was I2, right? I2. So let me write it right here. I2 is V minus AVD by Z naught. V minus AVD is what? Okay, plus A R1 V by R1 plus R2 divided by Z naught. This is I2. Now if we see, do I equals to I1 plus I2, we do it in the next page. I equals to I1 plus I2. So we had I1 was this V by R1 plus R2. R1 plus R2 plus I2 is what? I2 is this. So let me rewrite it simply. V1 plus A R1 by R1 plus R2 upon Z naught. It will be V1 plus A R1 upon R1 plus R2 whole upon Z naught. Okay, so let me simplify it further. R1. Okay, let's take V here. I by V. So I by 1 by R1 plus R2 plus R1 plus R2 plus A R1 upon Z naught R1 plus R2. So I've taken the LCM here. Then this will be R1 plus R2 plus A R1. And this R1 plus R2 will be multiplied at the bottom also. So this is this. Now again, if we take LCM here, will give us Z naught R1 plus R2. It will be Z naught plus R1 plus R2 plus A R1. Now, if we look back at the values, A was 1319, R1 was what, 19 kilo ohm, R2 was 23 kilo ohm, and Z naught was 399K. So A times R1 will be 1319 into 19. So it will be a much larger value. So here we can assume that A R1 is much greater than R1, R2 and Z naught. So in the numerator we can ignore these three, right? It will be thousands of times more than these. So what we have now is I by V equals to Z naught plus R1 plus R2 plus A R1 upon Z naught R1 plus R2, and we are ignoring these. So we have V by I by V equals to A R1 by Z naught R1 plus R2. Then give V by I equals to Z out equals to Z naught R1 plus R2 upon A times R1. It is Z naught 1 plus R2 by R1 by A. This is the Z out. Okay, so if we put the values, what we will get Z naught is, okay, 399K into 1 plus 23 by 19.
668. Okay.
Sorry, what did you say?
668K.
668.
Yeah.
Okay.
660.68K.
Yeah. Okay, so Z naught will be
670.21K.
sorry,
670.21. 670.21K, sir.
670.21.
21.
Okay. Now let's see what I was getting. Okay, so I was also getting 668 approx. Same thing. So let us see. So this should be the answer. And this there.
So I gain was 1319, sir. You have written 1316. That's why.
Where have I written 1316?
Finally,
Oh, so it should be 668 only, right?
yes, sir, it will be 668 then.
Okay. Oh, so, okay, there's no 668 in the answer. 658, 625, 691, 718. Okay. Let me check. Okay, fine. So they were approximated it as this only. So since this is the closest, you can mark this as the answer. I'm not sure like what will be in your with your values. Let me check. So the values given in your question are R1 equal to 17K, R2 equals to 23K, and Z out equals to 232, A equal to 1972. These are the values in your question this week, right? Uh, can anyone confirm if these are the values in your week assignment? So,
That is value, sir. Correct. Correct, sir.
on A. So what we will get here? 232 plus 23 by 17, 972, 276. So I'm getting it as around 276. So you should mark the closest one. I think that is 274.9 in your answer.
Okay, sir.
Yeah. Okay. So so one way you can see what you can see is like so here Z out earlier it was 400 kilo ohms. Now it has
I
reduced
think we should
to
include R1 plus
sorry.
R2 value. If we include R1 plus R2 value, then it can be right, sir. I think. We'll
Okay, so you
cancel
can
the three.
yeah you can check that. So if 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 let me write it. If we don't do this approximation here, R1 plus R2. Okay, I'm not erasing it. Let it be. So if we don't do the approximation, then what we will get Z out equals to Z naught R1 plus R2 upon A R1 plus R1 plus R2 plus Z naught. So
What is the value? 657, sir. Correct.
you're
657
getting
we are getting correctly, sir.
57. Okay, fine. So you can use this formula instead then. If the approximation is not valid in those results, please use this formula. Okay, so anyways, so what we have seen that so this Z naught earlier was what for approx 400 kilo ohms, right? But now it is reduced to some very small value, 668 ohm or something like that, like under a 1K value. So for a voltage amplifier, this is a very important characteristic, right? The input impedance is very high, but the output impedance is very low. So that is why op-amp in negative feedback is a very good amplifier. So negative feedback is actually stabilizing a gain by stabilizing Z out, right? Okay. So let us see the next question. Okay. Is there any doubt in previous question?
No, sir.
Okay. So in this question, what they're saying that if there is a ripple on the dirty power supply voltage, the op-amp allows the ripple through the okay through with a gain of this dB, and the gain is called power supply gain. Assume voltage across Zener diode is constant and does not change even with a ripple on the power supply voltage. What is the power supply gain of the regulator circuit? Give your answer in decibels. Okay, fine. Okay, so Here G naught is the power supply gain. Gain of system. It is given as minus 29 dB, and voltage across the inner diode is constant, does not change. Go to the power supply. Okay. So for any circuit, let's say if A, here it is B, in, out. So we know that gain becomes, uh, let's say gain earlier was uh, G, G naught. So new G with feedback becomes G naught upon 1 plus uh, A, B. If this was the open loop gain of A, then this is the feedback gain, then G naught is 1 upon 1 plus AB, right? Okay. So same will be done here also. So if G naught was the power supply gain earlier, so it will be A was the open loop gain. So here also A is the open loop gain, and B here beta will be one. Okay, the feedback gain that will be 1 plus R2 by R1. It should be right like this 1 by B. Okay. So anyways, this when this gain was open loop, so similar to what we did here, this Z naught was divided by this and done by this, right? Divided by open loop gain multiplied by the feedback gain. Similar thing will be done with this power supply uh, gain also of the op amp. So if we put it, what should we get? A is 1319, 1 plus R2 by R1 is 23 by 19, and G naught is 29 dB. So minus we need to first convert it to real scale. So what it will be? Let me see.
Zero point zero 0.03.
So this is 0.03. This is what you're seeing.
Yes, sir.
So how did you solve? Did you take 10 to the power minus 29 by 10 or 20?
20.
20. Okay, let me check. Okay, so fine. This is 0.03. So it is 0.03, and when we solve it, uh, okay, whatever we solve this, when we when we take in 20 log this value, we will get what we will get 84.51 minus 84.51. Okay, so this will be the answer here. G equals to 84.51 dB. Is it fine?
Yes, sir. Correct.
Okay. So in the next question, we have to find the uh, power supply rejection bandwidth. So we have to find the bandwidth that is of some frequency term. Okay. Okay. So are you able to hear me?
Yes, sir.
Okay. So we have to find the bandwidth here, and some problem has open this login. Trying to get connected. Okay. Fine. So it is given omega u equals to 11 megahertz, and op-amp model is ideal. Omega u by s. Now the power supply is this. Okay, so here we will have gs equal to g naught 1 plus r2 by r1 omega u whole upon 1 plus s 1 plus r2 by r1 uh, divided by omega u. Okay. So, okay, fine. So bandwidth. So, okay. So let us leave like where this is coming. Just uh, take it at is it at its. So, because currently I do not have the answer like from where this is coming, uh, but what they have said, right? So, So, so if you see how this uh, term connects with this, so they say that the power supply gain will be low at low frequencies. So that means that when S tends to 0, so this term will tend to 0, this term will tend to 0. We'll get what G naught into 0 upon 1, right? So it will, so G, so let me write when S tends to 0, G of S tends to G naught 0 divided by 1. So G naught, G of S tends to 0. And when at high frequencies, at uh, high frequencies, the power supply gain of the op amp at high frequencies, the op amp is low gain. Okay. Power supply gain will tend to be the native power supply gain of op amp at high frequencies. So at high frequencies, uh, GS will tend to G naught into something infinity upon 1 plus infinity some term. So this will be ignored and this part. So this term will be very high. This term will be very high. You can ignore one and these will cancel. So at very high, when S tends to infinity, G of S tends to G naught. G of S tends to G naught. So this is how like this relation confirms this statement. So anyways, now let us get back to like what we had to find, that is the bandwidth. So for bandwidth, simply we know that bandwidth will be just the uh, zero of this term, right? Sorry, pole, the root of this term. So bandwidth will be bandwidth equals to omega u upon 1 plus r2 by r1, right? So what were we getting when we solve this? 11 megahertz upon 1 plus r2 by r1 is 23 by 19. 1 plus 23 by 19 should get, I think, 4.97 megahertz is the bandwidth. So I know like this is not clear where this comes from, but I hope you can relate it with the question, what the question is being is asking you, right? Uh,
Okay.
okay. So I'll tell the next two questions also similarly. Okay. In question 4, uh, let the output and then no longer give a combination RNC. Okay, fine. Okay. So here Z out we had already find, right? So uh, this was our Z out. Let me copy this only. Okay, fine. So if we can separate it, so we can also write this as Z out equals to Z naught 1 plus R2 by R1 divided by A parallel with R1 plus R2. So essentially we had done this thing only when we were looking at here. Uh, yeah, so Z naught is this term parallel with this term, right? When we will invert it, it will come out to be similar, right? So this is what we are writing it in this form here. Okay, now what they're saying that uh, Z naught is now R upon 1 plus SCR times A. Yeah, which is omega u by S. Now, so now if we substitute this here, we will get Z equals to S1 plus R2 by R1 upon omega u dot R on 1 plus SCR parallel with R1 plus R2. Okay, okay, so we will put the value of Z naught here and the value of the A here. So this is the A term and this is Z naught. So this is our total Z. So now we have to separate so that it is a parallel combination of some resistance and some inductance. Yes, right. So if we do that, we will get R equal to 1 plus R2 by R1 upon omega UC parallel with R1 plus R2 and LE equals to R1 plus R2 by R1 times by omega U. Okay. So this is what it is, and yeah. So we had to find the inductor part. So this is the inductor part of the uh, impedance, and we have to calculate it. So R value is given 399K. R2 by R1 are same 23 and 19. Omega U is 11 megahertz. So let us see what is LE. So Okay, you can solve it later. So, but I hope you understood. So what we did, right? So earlier, uh, we had this, we replaced that. So now they have said that the output is a parallel of RNC where it is R is 399K and F is 2 pico. So it will be effectively this, and A, this model is given in question. So when we put all these, we'll get some formulation, and then we have to separate the parts that are the coming with S and parallel with the resistive parts. So if we do that, we get L, the impedance, inductance parts as this. Okay, so please see this one, and the next question is simply the resistor part, and this that will be given that by this. So the answer given for this is I think 12.76 millihenry, and for the resistance part it is given as 11.58 kilo ohms. So please solve these last two parts. And are there any doubts here? I know like we have not solved it completely, but any doubts in the procedure, like what we have to do?
No, sir.
Okay, so if you do, please feel free to message me. And with this, we can end today's session if we do not have any further questions.
So how to manage time in this exam, sir? If you
Sorry,
given long questions,
sorry, I didn't get
if
you.
you are given long question, how can we solve that? Use the time properly, sir, in exams, because
So
solving is very high.
yeah, so that is one issue. So first, you should practice your assignments carefully, as many of the questions are very similar to the assignment in your exam. And second thing is use approximations wherever you can make those approximations, because your if your exam if your questions are similar to assignment, it will be MCQ, and if you get close enough answer, you can eliminate the ones that are not required.
But we have a 20 marks for MS2 questions.
Sorry.
We have to fill in the for 2 questions, sir. That we have to fill in the
Most
type
of
questions of our 20.
You're saying there will be fill in the blanks type questions.
Yeah, yes, sir.
Yeah,
From
if
this
there are
session onwards, they are asking fill in the blank also.
yeah, if there will be fill in the blanks type questions, they will provide certain threshold that your answer should be near that, so it will be okay. It won't be like exact, you should get the exact answer.
Okay,
There will be like plus minus some deviation, it will work.
right, sir. But if you have a folded cascoding differential amplifier, how to solve that question? It requires a lot of calculation, right? Sir? In that, can you give some ideas for that question?
Which
Folded
question for?
differential. It is in assignment.
Okay, so the thing is that
Assignment
okay,
9.
segment 9. Okay, let me see.
Assignment 9 question 9. Assignment 6 question 9.
Okay, so oh, okay, so once you have you have solved your folded cascode, right? So it's not like that the folded cascode will change. This topology will always remain same, right? So once you have solved it, so why we were solving it step by step in class, that you should get the hang of it where the things are coming from. But once you have solved it, you can uh, see what from going from cascode to folded cascode, what is the effect of folding. So I think the swing and ICM these things change, right? So you need to just remember those things. You do not need to like solve every question from scratch at that moment. And the questions should not be such that you are not able to solve them in the given time. So it will be prepared uh, by the team of instructors carefully such that it is solvable. Don't worry about that. So these assignments
Right.
questions are given for you to solve in a whole week. They are not some 1 hour assignment, right?
Yes.
So the questions will be in the exam will be such that you can solve them in 1 hour.
Okay.
So all the best for your exam. And in between, if you have any questions, please feel free to contact me. And I may take some time to reply, but I will surely reply you. Okay. So good luck. And if there is no further questions, we can end today's session. Bye all.
Thank you, sir.
Thank you.
Thank you.
Okay. Bye guys.
Thank you, sir.
Thanks a lot, sir.
Yeah.